So let's continue with part 4, okay, of the chapter. So part 4, we will do a quick review on matrices and vectors, okay. So we have a quick review. Is not actually the in-depth understanding of matrices and vectors. We will deal with them in a future chapter, but here is just a quick review, something we have already known from previous years. Okay, so review things like how to add the two matrices together, how to add the two vectors together, to help us, as I said earlier or in a previous video, to help us to describe the solution set of a linear system, okay, and also here to help us perform Gauss's method more efficiently, and you will see it shortly, okay. So quick review on matrices and vectors. Okay, so let's start with matrices. Okay, part A, matrices. And let's start with some definitions here. Yeah. Definition. We have on M by N matrix. Okay. Is a rectangular array of numbers with m rows and n columns. Okay, so each number in the matrix is known as an entry. Okay, each element or number in the matrix is known as an entry. Okay, and yeah, let's see the last concept. Okay, a matrix is usually denoted with an uppercase Roman letter. Okay, and you know that. Okay, so we normally write an uppercase Roman letter to describe to denote the matrix. Let me give you a few notes here before we continue. Notes. Here, number 1. Okay, a matrix is usually denoted with an upper case Roman letter. So example, we have a B equals to 1, 2, 3, 4, 5, 6, 9, 10, 6. Okay, so if you pick this matrix, for example, how many rows do you have? 1, 2, 3 rows. And how many columns do you have? 1, 2, 3. So this is a 3 by 3 matrix. Okay, and we denote it with an uppercase Roman letter. A matrix entries are denoted with corresponding lowercase Roman letter. Okay, so matrix entries are denoted with corresponding lowercase letter. Okay, Roman letter. Okay, so for example, in we have the matrix yeah, in the B matrix. Okay, if I want the second element in the first row, so I have first row, second column. The element in the first row, second column is 2. I'm going to call it B1, 2. First row, second column is equal to 2. Okay, and I can also pick another one, maybe third row, first column. So I want the element B, which is located in the first row and in the third row and first column. So B31, third row, first column is 5. Okay. Okay, the third note. Yeah, the order of the subscripts matters. Okay. So and so maybe let me give here. Okay, let's see here. Okay, let me write it and show you the example. The order of the subscripts matches. That means B1, 2 is different from B2, 1. So here let me find B2, 1, B2, 1. I want the element that is in the second row, first column. So first row, second row, first column. So which is 4. So here B1, 2 equals to 2 and B21 equals to 4. Therefore, B1, 2 is different from B21. Okay, so the order does matter. Okay. The next note. The set of all m by n matrices is denoted by big M. So yeah, the set of all m by n matrices is denoted by big M like this with subscript m by n. Okay. Okay, there are some concepts we have learned previously that we need to adapt for the matrix as well. So one can perform Gauss's method using matrix in the same way as it is done for systems of equations. So one can perform Gauss's method using matrices, okay, in the same way as we have already done, okay, for our linear systems of equations. Done for systems of equations. Okay, so here are the concepts we need to keep in mind. You need to remember leading entries and the echelon form. Okay, if you remember leading entries, is the same as the leading variable when we discuss that concept regarding the systems of equations. Okay, we say that the leading variables are the first variables in a row that has non-zero coefficient, or that have non-zero coefficient. So a leading variable is the first element in a row that coefficient is non-zero. Okay, so the same concept when it comes to matrices. Instead of leading variable, we call it leading entry. Okay, a matrix rows, matrix leading rows, leading entry is its first non-zero entry or element, non-zero entry. Okay, its first non-zero entry. Okay, if it has one, very important, if it has one, because we may not have a row may not have a leading entry. Okay, a zero row has no leading entry if it has one. Another important point is the echelon form. Okay, and we can perform we can perform row operations to arrive at echelon form as well. Okay, you can perform a row operations, that means Gauss's method or Gauss's elimination. Okay, row operations to arrive at matrix echelon form. To arrive at matrix echelon form, where the leading entries in lower rows are to the right of those in the rows above. So basically the same concept we have seen for linear systems, and the reason why we can use matrix notation to perform the same operations is to make things easier and clearer. Okay, so you will see shortly with the example where the leading entry in lower rows are to the right of those in the rows above. Okay, so let me continue with a very important concept. Okay. Is the concept of augmented matrix. So number 2, augmented matrix. matrix or matrices. Let me give you the definition. Okay, let's say we are given a linear system. Okay, okay, a linear system of equations Okay, so let's write that linear system a11 x 1 plus a12 why did I okay, let's be a little bit neater. So a11 x plus a12 x2 plus dot a1n xn equals to d1. Let's say we have the following system, and up to m rows. You have m rows and n column. Okay, x1 plus am2 m2 x2 plus a mn okay xn equals to dn. Okay, let's say we have the following system of equations. So that system, okay, can be written or can be abbreviated. Okay, abbreviated. As you can see, we have too many terms or elements to write. Okay, can be abbreviated with an augmented matrix written as follows. So here is our, so basically we have a big matrix like this, okay, and okay, divided into two. On the left hand side we have the coefficients of the system, and on the right hand side we have the constants. Okay, so here we have the coefficient 1 1 and 1 1 2 dot 1 1 n. Okay, those are the coefficients, okay, of the system. And on the right hand side we have the constants d1. We do the same thing up to a m1 a m2 a m n d m. Okay, so writing a linear system in its augmented matrix form makes computations easier. Okay, so let me give you an example and then we will stop here. So let me show you example. Let's say we are given the following system. So let's say they say write the following system in its associated augmented matrix form. Okay, so we are given the following system: x plus y plus w equals 2 minus 2 minus x plus y plus z plus w equals to 2x plus 4z minus w equals to 5, and 3x plus y plus 4z equals to 1. Okay, in each augmented matrix form, we have the following. So we have our matrix. On the left hand side, we have the coefficient. So the coefficient of the x is 1, 1, 0. Here we have no term in z. That means its coefficient is 0. So we have 0z here and the w1. So here, that, and the constant on the right hand side is minus 2. Here we have second row, we have minus 1, 1, 1, 1, 2, and third row we have 2, 0, 4, minus 1, 5, and the last row we have 3, 1, 4, 0, 1. Okay, so that's the augmented matrix form of the linear system. In the next video, I will do a tutorial about how to perform Gauss's method on an augmented matrix. As you can see, it's going to be the same procedure as for systems of equations, but the advantage of augmented matrix is it is less computation, is less expensive computationally. Okay, so I think I'm going to stop here, and I will see you in the next video for a tutorial. Okay, thank you, and see you.